This chapter we've been looking at redox reactions, and for this quiz we're going to start by defining oxidation and reduction in terms of electron transfer. And just as a reminder, redox is a shortening of the terms reduction oxidation, so they're very much important for this type of reaction. In terms of electron transfer, it's pretty straightforward. Oxidation means losing electrons and reduction means gaining electrons, and because we have electron transfer, these two processes always happen together. Something is losing electrons, being oxidized, something else is gaining electrons, that's where those electrons go. And there are a lot of ways to remember this for students. I think this oil rig is a useful one. Oxidation is losing, reduction is gaining, that's one way. And I think my favorite way of remembering this is that reduction means that the charge of the oxidation number is going down, it's reduced, becomes more negative. This is because you're gaining electrons. Electrons are the negative particle. Okay, now we want to look at the following reaction and identify what's being oxidized and reduced in this reaction. And here we have zinc solid and copper 2 plus that becomes zinc 2 plus and copper. And so if we look at this, we can see that zinc on one side is becoming zinc of a different form on the other. And in this way, it's losing electrons. We have solid zinc, elemental zinc, that's becoming zinc 2 plus. And this occurs by losing 2 electrons. This is oxidation, right? We've had 2 more electrons before, now we've lost those 2 to form zinc 2. Copper 2 is becoming copper, and this represents a gain of electrons, where we have first the plus 2 charged copper, and it is gaining 2 electrons to have a charge of 0, and this is reduction. And this is a pretty straightforward example, but is a really great way to determine which is reduced and which is oxidized in a chemical reaction. Another way is that we can assign oxidation numbers, which in this case is relatively straightforward as each of these are basically monatomic and therefore the charge is the oxidation number. We'll have a little bit more on assigning oxidation numbers in the next question, but this also shows these numbers very deliberately. Zinc goes from 0 to plus 2, showing that it is being oxidized. Copper 2 is reduced here, that's the reactant that's reduced, and in order for it to be reduced, something else has to be oxidized, right? We can view this as solid zinc is losing its electrons, and in doing so is causing something else to gain electrons, to be reduced. And therefore we say that zinc is the reducing agent. It's what causes reduction to occur. Zinc is oxidized because of copper 2 plus conversely, and so while copper 2 is what is reduced, it is the oxidizing agent because it causes oxidation. And this is an important distinction here as well. It kind of seems like, well, it's the opposite, but remember that when we say agent, we mean that it's causing that effect to occur. Okay, now we have another reaction and we want to assign oxidation states to all elements, then determine the total electrons lost by the oxidized species and the total electrons gained by the reduced species. And as we look at this question, we think about the total electrons. Remember that they should be equal, right? It's a transfer of electrons, so whatever the number is that's lost by the oxidized species, it should be that many that are gained by the reduced species. And so I think a good way to start is with our oxidation numbers. And here, iron is by itself, therefore it's 0, equal to the charge is 0, oxidation number for iron is going to be 0. What about chlorine? Well, again, it's by itself, and therefore oxidation number is going to be 0. This is oxidation number 0, chlorine, oxidation number 0 for iron. But on the other side now, we have an ionic compound, and each of these is going to have oxidation numbers equal to their individual charge within the species. And here that's going to be plus 3 for iron, which we determined because we know that chloride is always minus 1, and there are 3. And so as such, we've determined our oxidation numbers for all the different species in this compound. Halogens, chlorine, fluorine, whether they're an ionic or molecular compounds, they tend to be -1. Okay, from this we can see that iron is what's oxidized. It goes from 0 to positive 3, and chlorine is reduced. It goes from 0 to -1. We have something oxidized and something reduced. But note that iron is losing 3 electrons, but there are 2 iron atoms altogether. Because if we kind of just look at what's oxidized and reduced, it looks like iron is losing a lot more electrons than chlorine is gaining. However, when we take into account the fact that there are 2 iron atoms participating in this reaction, it's 6 electrons that are lost by iron. Each chlorine atom is gaining 1, but there's actually 6 chlorines within this reaction, and so it's 6 electrons gained by chlorine. And the number is equal. This is a very important thing to be able to keep track of for moving forward in electrochemistry. When we look at this reaction, What we see is the transfer of 6 electrons, and we can determine that just based on the balanced chemical reaction and breaking it down a little bit. Okay, finally here we have an unbalanced redox reaction, and we want to use the half reaction method to balance the equation. And when we look at this, there's a lot of problems, right? There's only oxygen on one side, the charge doesn't look like it's balanced on each side, and it's not going to be as easy to balance this with our regular methods as we've done, since the beginning of chemistry. And while this wasn't really part of the instructional video, it's part of the reading, and here are the steps that I would take for balancing a redox reaction. And the first thing is what we've done before, assign the oxidation states. Let's skip the manganese for now because it's a little bit more complicated, but the iron here is pretty clearly +2, manganese on the product side is +2, and iron on the product side is +3. And going back to the permanganate, what we have here is oxygen, which likes to be -2 in a compound. If oxygen is -2 and there's 4 of them, altogether that's -8. The whole complex has a -1 charge, so manganese has to have a number that, when considered, will make the charge -1. And that's going to be +7. +7 minus the 8 that come from the 4 different -2 oxygens gives us a negative charge for this polyatomic ion, and therefore this is +7 oxidation number manganese. Now we want to determine the oxidation reduction half reactions. We can do that based on these charges, seeing what's oxidized, what's reduced. Manganese is going from +7 to +2, that's reduction. Iron is going from +2 to +3, that's oxidation. And we want to break apart these two half reactions to show an oxidation and a reduction. Next, we want to balance with respect to non-hydrogen, non-oxygens, and they're actually both balanced here. 1 manganese and 1 manganese, 1 iron and 1 iron. Step 4, we want to balance the oxygens using water. The iron equation is actually just fine, but in the top equation, we want to add 4 waters to the right side. It's going to throw off the balance of hydrogen, but that's okay. We need to make sure we have 4 oxygens on each side for this step. Because next, we're going to balance the hydrogens using H+, protons. Again, the bottom reaction is just fine, but in the top reaction, we need to add 8 protons to the reactant side. Now we have 8 protons, 8 hydrogens on each side. Charge is not yet balanced, so now we're going to balance each one using electrons. If we look at the charge, we'll see that we need 5 electrons on the left. That makes the charge on each side equal. And on the right, we need a single electron for that bottom equation. Now we're almost ready to add the two together, but we need to make sure that the electrons don't appear in the final equation. And so we need to scale up one of these to make sure that the electrons cancel out and represent the correct number of electrons being transferred. The top equation is going to be fine. The bottom half reaction, let's multiply everything by 5. And once we do that, if we add the two together, we get our final balanced chemical reaction where electrons do not appear, right? Remember that electrons are transferred within these reactions. We don't want to show any consumption or creation of electrons. We want to show a balanced chemical reaction where if we look at this, there's the same number of each atom on both sides and the charge is equal on both sides.